Right, so this week we're having a break from this story that we've been building up over the last few weeks, this story of calculus shading into analysis. We've taken that up to a certain point in the, well, more or less up to the beginning of the 19th century. And I'm going to come back to that next week. But for this week, we're having a sort of algebraic interlude. So the two lectures this week are algebra as equation solving in the first half, and then algebra as in sort of the more abstract ideas like group theory and related areas. So that's what I'll cover in the second half. So we've almost not acknowledged algebra so far in the course. Certainly I was talking about symbolic notation in earlier lectures, but there's some sense in which it's sort of so fundamental to what happens in mathematics that you could maybe easily overlook a lot of what goes on with algebra. So I'm going to try and pull out some of that in this lecture. As you can see, another quite ambitious time span to cover in a single lecture, but I'm going to work through fairly systematically. So I will start with quadratics and then move up to cubics and quartics, and then various things that people are saying about equations in the 16th century, and then on through 17th, 18th, and then we'll stop and we'll sort of take stock of where we are before we then launch into the 19th century in the second half, and see how things are becoming more abstract at that point. So I'm going to start, as histories of algebra, as histories of mathematics often start, with something from a cuneiform tablet. This is from about 1800 BC. This, I think, is in the British Museum. And it's a text where essentially we're completing the square. So it's solving a quadratic equation. And it starts like this. It says a reciprocal exceeds its reciprocal by 7. What are the reciprocal and its reciprocal? Okay, so there's lots of reciprocals there. So we need to, first of all, know what that means. Well, as you probably know, we're working in a base 60 system in this context. And the reciprocal is referring to two numbers that multiply together to make 60. So this is what we're looking for. So essentially two numbers that multiply together to make 60 and that differ by 7. I should say that in what follows, I've simplified the notation slightly. So this is in Mathematics Emerging. If you have a look there, you will see that this is all worked through in terms of sexagesimal fractions. I've shifted to ordinary, from our point of view, ordinary fractions, just for the purposes of this slide, just to make it a bit simpler. Okay, so how do we start? Well, 7 is one of the only things we can get hold of. So we're told that we break the 7 in half, and that gives us 3.5. We multiply the 3.5 by 3.5, and we get 12.25. We append 60, which interestingly is referred to as the area, to 12.25, and we get 72.25. And then still perhaps thinking of this as an area, we're asked, what is the square side of 72.25? So what is the square root of 72.25? We work that out and it's 8.5. We write down 8.5 twice. We subtract 3.5 from one of them. We add 3.5 to the other one. And lo and behold, we've got 5 and 12, which are two numbers that differ by 7 and that multiply together to make 60. So there are various things to comment on here. There's clearly something geometrical going on in the background, even though if that's not stated explicitly. There's some sort of cut and paste geometry. And at the same time, this is probably intended as an adaptable example. So we talked about this previously, where people are not writing down general solutions to problems, general proofs of theorems. They're writing down one example, but it's not necessarily intended as a single example. It's something for the reader to be able to adapt for themselves to other situations. And so possibly that's what's going on here. And as for the sort of the cut and paste geometry of it, we can draw some pictures to see what's going on. So if you see at the top left there, we've got the unknown, so the smaller reciprocal, and then unknown plus 7 along the top edge of the rectangle. We're breaking the 7 in half, moving that width 3.5 segment around to the side, and then quite literally completing the square at the bottom there by adding this 3.5 by 3.5 square into there. So there's geometrical thinking behind this, and there are various points to note as we continue with the discussion of algebra, and this is something we'll pick up in the classes as well at some point, I think. So we're used to thinking of algebra as being this very symbolic equation-based thing, but of course at no point have I written down an equation of any kind. So I still say that this is algebra, but of course it's not algebra in quite the same way that we're used to. There's a recipe for the solution, which seems to come from some sort of geometrical insight. And as I've just said, it's not explicitly a general solution, but perhaps it's intended as one. And so, again, so a point to pick up elsewhere, perhaps, is the idea of geometrical algebra, which I don't know if any of you have come across that in the reading, but this is very much a late 19th century idea when people are starting to read these texts, that they're sort of, I would argue, projecting backwards and saying, oh, well, there's obviously some algebraic thinking going on here, even in things that are more overtly geometrical. And so they're trying to attribute algebraic thinking to texts where we might question whether it's actually there. And it's an idea that doesn't go away. So it's something that people still argue about. So we have that sort of background in sort of ancient Babylon, and we can jump forward many centuries to Diophantus in the 3rd century. So this is somebody, of course, I've mentioned before in connection with the transmission of ancient Greek texts to the early modern world, to early modern Europe. And this is a text that is very much more based around problems that we'd call number theory or algebra nowadays. So in contrast to more geometrical texts by Euclid and Apollonius and others. So for example, Book 1, problem 27 says, find two numbers such that their sum and product are given numbers. So actually it's a bit like the Babylonian problem that we just had. And in fact, the solution recipe is not a million miles away from what was being done before. So this is worked through as finding two numbers that add to 20 and that multiply together to make 96. Leave it as exercise for the reader as to what those numbers actually are. But as I say, the recipe for finding the solution is not hugely different from what we've seen before. Okay, skipping still further ahead to another familiar name. So we have Al-Khwarizmi, who hailed from a region now in modern day Uzbekistan. But of course, he's part of this sort of house of wisdom that we talked about before. He's interested in solution of equations, and he publishes this text whose title translates into English as Book on Restoration and Balancing. So restoration is the idea that you have an equation, and all expressed verbally, but if you have an equation and you have something negative on one side, the act of restoration is adding something positive to get rid of the negative thing. And balancing is you do the same thing to both sides of the equation. And the restoration part of the title is algebra. And so that's why we get the word algebra from. So to a very large extent, Al-Khwarizmi is working in a mathematical world where he doesn't use negative numbers. I mean, he acknowledges them. They're often in there with an indication of this is where things go wrong. So we're not interested in them, but they're there. But mostly he's working without negative numbers and with zero. So with those restrictions on what you're doing, you can see that we end up having to do a case-by-case treatment of the quadratic equation. So squares equal linear term, square equals constant, and so on. And then, of course, we can roll the linear one in there as the case where the square is zero. And for each of these, he gives a recipe for producing the solution to the problem. And he's working mostly arithmetically, but as you can see here, this is just one page from a version of the text. So this deals with case 4 from here. So square plus linear term equals constant. He's still giving you some geometrical justification. So he's not trying to prove things geometrically, but he's he's justifying, motivating what he's doing by throwing a bit of geometry in there. And as you've probably guessed, the use of the word algorithm here is deliberately chosen. When these texts are translated into Latin, Al-Khwarizmi's name is rendered as algoritmus, and each of the problems is set out with the words dixit algorithmi, so says Al-Khwarizmi, and so the word algorithm comes from here for this sort of fixed procedure for solving a problem. As we've also already seen, these sorts of ideas coming from the Middle East, they're finding their way into Europe, up through Spain and Portugal, but also through Italy in sort of around the 12th century, with people like Leonardo of Pisa, aka Fibonacci, traveling out into the Middle East as traders, bringing ideas back. And Fibonacci in particular writes this book, Liber Abaci, the Book of Calculation, and it includes, for one thing, it includes Al-Khwarizmi's recipes for solving these different types of equations, lots and lots of examples, geometrical justification, doesn't go very much further than that, but of course it's beginning this process of transmission of ideas from the Middle East into Europe, including a nice new set of numerals that are at this point not yet really very well known in Europe, so Indo-Arabic numerals that he lists on this page here. So this, for many people, this is where they're learning about these numerals for the first time through Fibonacci. I mean, there are other sources as well, but he often gets a lot of the credit. So these ideas are spread quite readily across Europe. So by the time we get to the 16th century, Al-Khwarizmi's rules for solving these various types of equations are quite well known. They're sort of part of a mathematical toolkit. And that's for quadratics. So once you've got quadratics, people then do start to think about what happens with higher equations. So for cubics, we have to move to Italy in the 1520s. So people start to look at equations of that form. So x cubed plus px equals q. There's no square term. I'll come back to that point in a second. But this is something that people investigate. So, for example, a general solution is found by a man called Scipione del Ferro in Bologna in about 1520. And he doesn't publish this because he's in an academic world where there is competitive problem solving for people to advance their careers in Italian universities. So he's got a nice new tool for competing in these competitions. So he doesn't publish. He does, however, teach it to a couple of people, so a pupil and to a son-in-law. But then it's rediscovered independently by Tartaglia, who's probably so far the most familiar name on the slide, I would guess. And he beats one of them, Fiore, I think. He beats him in one of these contests because he's devised the same rule for solving the problem. And Tartaglia eventually passes this solution in rhyme to Cardano. So Cardano, another sort of famous name here, I suppose. He's writing a textbook on the solution of equations, or he's writing a textbook on algebra, maybe I should put it that way. And he's trying to pull together various pieces of information. Tartaglia gives him the rule, but he says, well, please don't publish it, because Tartaglia himself wanted to publish this. And so Cardano doesn't publish it, and all is well, at least for the time being. So he passes it in rhyme, and the rhyme rendered into English looks a bit like this. So when the cube and the things next after together equal some number apart, find two others that by this differ, and this you will keep as a rule, that their product will always be equal to a third cubed of the number of things. The difference then in general between the sides of the cube subtracted well will be your principal thing. I'm going to assume it works better in Italian, but let's pick that apart. So when the cube and the things next after, so we've got the cube and px is the things. So there's the Italian word lurking in the background here is cosa for thing, and then that sort of spreads into other languages as algebra comes to be known as the Cossic art. The Cossists are the people who do this kind of thing. So anyway, the cube and the things next after equal to some number of parts, so equal to q. find two others that by this differ. So find two numbers that differ by q, then their product will always be equal to a third cubed of the number of things. So the number of things is p. So u times v is p over 3 cubed. So we're into the realms of something very much like Diophantus here again. We're looking for two numbers that differ by something and that multiply together to make something else. And then the rule says the difference then in general between the sides of the cubes, so the cube roots of these two things, will be your principal thing. So this is x. Okay? And this, in fact, is more general than it would appear to be. So there's no squared term there, as I commented on. Well, in fact, you can always suppress the squared term in a polynomial like this. So this is actually, allowing for negative values and so on and so forth. This is a general solution to that polynomial and to other cubic polynomials. In modern terms, this is what one of the solutions looks like. And it's a solution in radicals. So it uses addition, subtraction, multiplication, division, and the taking of roots. So in this case, square and cube. And this is a legacy of the sort of classical ruler and compass construction methods. Because if you try to handle numbers using ruler and compass, it's these kinds of quantities that you can construct. So these are the terms in which people continue to seek solutions to these polynomial equations. So here for cubics, and later for quartics. And of course, if you think about the quadratic formula that we all know, that also is a solution in radicals. So these are the terms in which people are looking for solutions. So Cardano published his textbook quite early on, didn't mention Tartaglia's work, but later still, he wants to publish a comprehensive text on algebra. So the great arts or the rules of algebra is this text that he eventually produces in the middle of the 1540s. And of course, he wants it to be comprehensive. He wants to include the rules for the cubic that he got from Tartaglia, but he promised he wouldn't publish them. So he does something that is either clever or sneaky, depending on your point of view. He sort of heard tell of some of the other people on the list before. So Del Ferro, for example, Cardano goes off to Bologna and he finds Del Ferro's papers, and in those he finds the solution to the cubic, and then he publishes from there. So he doesn't, strictly speaking, doesn't publish what Tartaglia told him, but he publishes a version of it, and Tartaglia is not happy about that, really. So this text looks at equations in general, so certainly it looks at cubics. It enumerates the cases in the same way that we saw with Al-Khwarizmi. So we're enumerating number equal to square plus thing, number and thing equal to square, and so on. So that the quadratics are rolled up into this cubic list where the cubes are 0. But these are all the different cases that he looks at. And if we just look at one of them, for example, so on cubes and things equal to numbers, so this is the case that we were just looking at in Tartaglia's rhyme. Cardano gives us a recipe for doing this. You can see in the first paragraph, he's giving a bit of background. So he mentions Del Ferro, he mentions Tartaglia. And we can also see that he's giving some geometrical justification there, as ever. So he's not proving it geometrically, but he's motivating it that way for the reader who is more familiar with geometry. And we have something new. So he's not working through a specific case in order to illustrate how you might generalize that to other situations. He is actually giving a solution in general terms. He's managing to phrase it that way. It's entirely verbal, which makes it difficult to follow, but it is a general solution that he's giving in the proper sense of the term. And there's also something else that's going on here. So I've already mentioned that in a cubic you can always suppress the square term. Well, Cardano's doing that. And so it's sort of interesting that he's not simply diving into equations and setting out to solve them. He's thinking about how you might manipulate them prior to solving them in order to put them into a more amenable form. And so this is something slightly new going on here. So he tends to stay with positive values. He acknowledges that there are such things as negative values, but tends to steer clear of them, maybe use them as an indicator of where things have gone wrong, or where a solution doesn't have or a problem doesn't have a real world solution. And he acknowledges imaginary quantities as well, but keeps them very much at arm's length. And this is something that I will come back to in a couple of weeks when I've got a lecture on complex analysis, and at that point I will go back and say something about complex numbers rather than doing it here. So the Ars Magna doesn't just go up to cubics, it goes up to quartics, and this is where Cardano's student Ferrari has quite a lot of input. So he finds a general solution for at least some of the cases of a quartic. Mostly here in the form of worked examples, though, because excuse me. Of course, once you move into the case of quartics, you've lost any hope of geometrical interpretation. It's difficult to visualize things. The way that the methods work mean that you start to need to introduce a second unknown quantity. And although it's not impossible to keep track of two unknowns whilst doing things verbally, it's a bit of a pain. So it just makes it a bit more difficult to just to work through things verbally. So I'm just going to give you an example of how one of Ferrari's methods works, because it has some relevance for things that come later. So again, we're going to look at a specific case of a quartic, so something of this form, so no cube term. And so what Ferrari does, he says, well, let's introduce a second unknown, and we'll call it y. And all this is in entirely modern notation. This is very much not how he wrote it, but we add 2yx squared plus y squared to both sides of the equation. And the reason we do that is because it then makes the left-hand side into a perfect square. And then we gather like terms on the right-hand side. And of course, now we've got a square on the left-hand side. We think, aha, wouldn't it be nice if we also had a square on the right-hand side, and then we could just take square roots and we could solve this thing. So what condition do we need on the right-hand side for that to be a perfect square? Well, we need the sort of b squared equals 4ac in the quadratic formula. And so if you investigate when that will happen, you find that it will happen precisely when y satisfies this equation, which quite clearly is a cubic. So we started out trying to solve a quartic, and we've reduced it to a cubic. And in principle, we know how to do this now. So we can solve the cubic, we can put the right value of y back in at the top, and then sort of work through and solve the quartic. And much the same as before, this is actually more general than it would appear to be, because in any quartic, you can suppress the cube term with an appropriate substitution. Which is something that Ferrari and Cardano explore. Okay, so there are two things here. There's this idea of substitution, there's change of variables, and all of that is part of this manipulation of equations prior to solution, which is a sort of a departure from this very much more rigid recipe for solving equations. I haven't put the quartic formula on a slide because it doesn't fit nicely. It's something that everybody should see once, but then move on very quickly. But anyway, it does exist, and if you have a look at it, you'll see it's a solution in radicals. So it involves now fourth, cube, and square roots, and then basic operations. Okay, so I think I acknowledged maybe in an earlier lecture that Cardano, he's writing in terms that are quite alien to us, so we find him difficult to read, but even his contemporaries found him quite difficult to read. So you find people in the later parts of the 16th century reinterpreting and tidying up things that Cardano had said, and in particular Raphael Bombelli publishes this text. It's in Italian, so these ideas are spreading to a sort of wider readership. They're not sort of the Latin reading academic class. They're sort of getting out more widely. And he sort of repackages a lot of what Cardano was saying in a slightly easier form. I've put here new notation because exponent notation is something that may come from Bombelli, where he's trying to sort of simplify things slightly. And he explores complex numbers a bit more systematically than Cardano. And he's a bit ambivalent about what they are, but he comes up with some rules for how to handle them, and we'll see that in a later lecture. Around a similar time, we also have Simon Stevin, which is a name that might be familiar to you because he's tends to be remembered as the person who gave us the system of decimal fractions that we now use. And so he produced this text on arithmetic and algebra. It's got Al-Khwarizmi's rules in it. It's got some digested version of Cardano's and Ferrari's rules. And at the end, he, as an appendix, he puts his treatise on decimal notation. And so this is where that starts to spread from. And so we're getting up to the beginning of the 17th century. So we're coming back to some of the figures that we've seen before. So Francois Villette, we've already mentioned in connection with symbolic notation. And of course, he's using symbolic notation because he's doing algebra. And so we saw this link being established between algebra and analysis, algebra and geometry, algebra in this case called analysis or the analytic art. And when it comes to solving equations as well, he's also exploring the ideas about solving equations numerically as well, if you can't find an exact solution. Okay, so having mentioned Villette, I also need to mention Thomas Harriot and somebody else that we've seen before, somebody else who's interested in using symbolic notation to streamline his mathematics. And one of the big things that Harriot does is something that's so fundamental to how we handle polynomials, but it's a new idea at this time, is he starts writing them and breaking them down into linear factors. So you can see this is what he's doing at the top left-hand corner there. So A is his unknown. So he's got 4 linear polynomials in A, and he's multiplying them together to get the thing that's in the middle at the top there. And so this is just something that you don't see if you are handling these things verbally. As soon as you start writing them down in this form, you start to see these kind of interconnections. And you can build up ideas in the way that we do. We can relate the coefficients to the roots. We can start talking about the nature and number of the roots of an equation in a much more systematic way. So some of this makes its way into published form. So Harriot's manuscripts were circulating privately throughout the British Isles in the sort of first half, well, throughout the 17th century really. They go missing for a while and there's a big hunt for them. But anyway, so some of his ideas are published posthumously in this text, the Artis Analyticae Praxis. But his editors are considerably more conservative than Harriot himself, because as we'll see in a later lecture, he makes free use of imaginary roots. He has no qualms about employing these in his mathematics, but his editors didn't like that. They take away the imaginaries, they cut back on the negative ones as well. So this is a sort of a more restricted form of Harriot's ideas. But as I say, the manuscripts are circulating privately, so those ideas are getting out there. And Harriot tends to be sort of lauded by various people writing on the history of mathematics in the next couple of centuries. So this is Charles Hutton, so quite some time later, but he published this Mathematical and Philosophical Dictionary, which is, you could argue, is an early attempt to write some history of mathematics. And he sort of waxes lyrical about Harriot and about how he, showed the universal generation of all equations by the continual multiplication of simple ones. So this is recognized as being quite a big deal. We'll also see in a later lecture that John Wallis, when he writes his treatise of algebra in 1685, he also has a lot of praise for Harriot. Not unbiased praise, it has to be said. He claims that Descartes plagiarized Harriot, and this is all part of creating the idea that algebra is something that was invented in England. But anyway, we'll come back to that in a later lecture. So what you might be picking up on then from this sort of whistle-stop tour of where things are going into the 17th century and beyond is that there's a change happening in the 17th century in that algebra is going in two different directions. We could maybe pull out algebra that remains the way it always has been. It remains a tool, it's analysis, it's the analytic art, it's what the cosists do, it's solving equations, plain and simple. It's just a technique for taking an equation and finding an answer. But there's also something that's emerging that we might call the theory of equations. So an understanding more of the structure of equations. So not just solving them, but understanding how they're put together and identifying how many roots they will have and things like that. So these two slightly different kinds of algebra are emerging. And you get a good sense of some of this from, yeah.
Because calculus was also developed in 1600, was it considered part of algebra?
Yes and no. It depends how you are coming at it. So if you're Leibniz, then pretty much yes. As far as the finite aspects of it are concerned, there's a bit more of a concern about where the whole thing about infinitesimals sits. If you're Newton, his attitudes change, but he's thinking more algebraically at the start, but then he retreats into geometry, and algebra becomes this useful problem-solving tool, but not proper mathematics. So, yeah, there's a much longer answer to the question as well. It's not an easy question to answer. So, okay, so in terms of theory of equations, we see a lot of this in Descartes' geometry. So, for example, he has the same ideas as Harriot, that you can build up polynomials from linear factors or simpler factors at least. And this is where Wallace jumps in and says he's obviously plagiarizing Harriot at this point. I'm not sure there's any great evidence for that. And Descartes also introduces other things that very definitely come under the heading of the theory of equations, so the rule of signs. I don't know if this is something that you will have ever met, really, but perhaps not. So it's to do with the number of times that the sign changes as you move from one term to the next in a polynomial. So the number of times it changes gives you an upper bound for the number of positive roots that the equation can have. So in this example, we go from positive to negative here, negative to positive, positive to negative. So that's 3 changes of sign. So there are at most 3 positive roots to this equation. And that can all be justified. But at this stage, this is sort of something that Descartes noticed as a useful tool for how to handle equations. And he also has things that sort of pick up on the things we saw with Cardano, say, where you can always suppress the n-1 term in a polynomial. So you can always make that simplification if you're trying to sort of build up a wider theory. He also does things that we would now regard as being quite sensible. So if you're trying to factorize a cubic, well, look at the factors of the constant term to give you some idea of what to try as a factor. So, if alpha is a factor of the constant term, then try x minus alpha as a divisor of the polynomial. We've got an example on this slide here. You might, it's not great, but you might just be able to make out Descartes' equal sign, the one that to our eyes is slightly unusual. And this is the example that he works with. And you might notice that there's something unusual, well, maybe slightly unusual going on with this equation in that, yes, it's on the surface of it, it's a 6th degree equation, but it's actually cubic in y squared. And that will become relevant in a moment. He also looks at quartics, and he sets out here to solve the equation that he writes in that form, and that we would write in that form. And the way he approaches quartics is he tries to write it as a product of 2 quadratics. And so he sort of writes down some equations, he expands out, he equates coefficients. Out of all this emerges another equation that needs to be solved in order for you to find those coefficients. And it's a more general version of the equation that we just had. So again, it's cubic in y squared, which means that he started out trying to solve a quartic and he's ended up with a cubic, which in principle he knows how to do more easily. So again, we've got this sort of reduction of degree as being something that's part of the way of solving things. Okay, so these are the sort of ideas that are already circulating by the middle of the 17th century. And just to repeat what I said before, people are looking for solutions of equations and they're always looking for them in terms of radicals. So basic operations and roots, because of this legacy of ruler and compass constructions. And so we've got solutions in radicals for quadratics, we've got them for cubics, we've got them for quartic equations. I'm sorry if this comes as a surprise or a spoiler for everybody, but hopefully you already know that the general quintic equation is not solvable in radicals. But people, of course, they're continuing to try to find a solution in radicals, and unfortunately they're not really getting anywhere. And so by the 1770s, certain people, and most particularly Lagrange, who we'll come to in a moment, is beginning to suspect that the reason that people are not getting anywhere is because it can't be done. It just seems to defy all the same sort of methods that are used for other equations. And so from Lagrange, though, we start to get this idea, this idea takes hold that actually between Cardano and then between something that Lagrange writes in 1770, Lagrange asserts that nothing interesting has happened in algebra. So it really sort of takes hold as an idea in various writings. So this is from a book on the history of modern algebra by mathematician Luboš Nový, who says that from the propagation of Descartes' algebraic knowledge up to the publication of the important works of Lagrange, which we'll come to shortly, the evolution of algebra was at first glance hardly dramatic, and one would seek in vain for great and significant works of science and substantial changes. If you've read around this topic, this may be an attitude that you will have found. But of course, in the first lecture, I warned you to always be suspicious about what mathematicians say about the history of their subject. And so, is this a fair point? Maybe not. You may guess from the very fact that I put it here that I'm going to now disagree with it completely. Because there are other interesting things going on in these centuries when it comes to understanding the structure of equations. So, for example, Hutter's rule that you might have met at some point. So Jan Hutter is sort of connected to Franz von Schoten, who produced the Latin translation of Descartes' geometry. What very little remains of Hutter's writings is appended to this Latin translation. So we don't know a huge amount about what he was doing. But he takes a polynomial of that form, for example. He multiplies the terms of the equation in turn by an arithmetic progression. This turns out to be kind of a useful technique for him. So, for example, in this instance, he multiplies the terms successively by 3, by 2, by 1, by 0 as his arithmetic progression, and gets the equation that starts 3y cubed. He then uses the Euclidean algorithm to find that the greatest common divisor of these two polynomials is x minus 1. And he deduces that the original polynomial is divisible by x minus 1. So if you've seen Hutter's rule, you'll have seen it as a technique for identifying double roots of a polynomial. Nowadays, it has a phrasing in terms of the derivative of the polynomial, because what you might notice is this here is essentially x times the derivative of the polynomial that we started with. So there's some sort of shade of calculus going on here, but of course this is before any of the techniques from calculus have been formalized. Okay. Elsewhere, We could look to the work of Ehrenfried Walter von Schönhaus. He's also trying to simplify equations. He's trying to break them down, make them be more amenable to study. And in his case, it's about the systematic removal of terms. So we already know, as we've said, that we can suppress the square term with an appropriate substitution. And he says, well, can we get rid of any more terms? And the answer is yes. We can get rid of both, in this case, both the square and the linear term with an appropriate substitution. So Schönhaus says, oh, this is great. And of course, I can extend this method to higher powers. He didn't actually try it, though. In particular, he didn't try the case of a quintic, which is where this all starts to break down. But he's sort of, it's a nice method that works for low degrees. We also have a text by Newton, 1707, the Arithmetica Infantorum, which is based on lectures that he gave as Lucasian professor in Cambridge. It was put together by his successor as professor, William Whiston, not entirely with Newton's blessing. I think that he sort of grudgingly agreed to it for one reason or another, but was never particularly happy with the result. And it has to be said that if you are learning arithmetic and algebra at the beginning of the 18th century, this is really not a good book to do it from. And so there are lots of texts that follow on in the 18th century in Britain that are sort of responses to this, that sort of try to tidy up what Newton was saying, make it a bit more comprehensive, whilst also doing the dance of always being respectful to Newton. But anyway, so he has any number of things in there that belong to this theory of equations. So these sort of rules that you might have seen before, possibly on a prelims problem sheet at some point. So rules for relating the sum of the roots to the coefficients, the sum of the squares of the roots, the sum of the cubes of the roots, and so on. And he does other things like he produces an extension of Descartes' rule of signs that we just saw to try and put a bound on the number of complex roots that an equation can have. So Newton is fully acknowledging the existence of complex solutions, but to him they are always a sort of marker of a problem not being applicable in the real world. So he has sort of a negative view of them. So this is just a few examples of what's happening in the 17th, 18th century. And so you could argue that sort of by the end of the 17th century, okay, people have solutions for quadratics, cubics, and quartics. They don't have any higher degrees, so they don't have any more solutions than that. But in a sense, they have more information. They have more knowledge of how equations are put together, even if there are some that still can't be solved in general. So to summarize then, so 17th, 18th centuries, as we've seen, we've got the beginnings of symbolic notation. We've got this understanding of the structure of polynomials, the nature and number of their roots, and people are beginning to suspect that such a thing as the fundamental theorem of algebra might hold. It's a long time before anybody proves it, but you know, nobody has come up with an example of a quartic equation with 5 roots, for example, and so people are beginning to suspect that there's a very natural bound on the number of roots of equations. And then once you're into sort of Harriot's language of writing things in terms of linear factors, then it sort of becomes more obvious that this bound is there. And it's one of the things that leads people to start to accept complex roots a lot more, because it gives you this nice, neat formulation of the fundamental theorem of algebra as an exact number rather than as an upper bound for the number of roots. Okay, yeah, relationship between roots and coefficients, how to manipulate them. I haven't gone into this in any detail at all, but people are also investigating numerical solution of equations. And so you could argue that in the same way that we were seeing with calculus, people are leaving behind geometric intuition, going in a more algebraic direction. Here too, the geometry is being left behind to some extent. Yeah.
When we discuss like format and limits, you see that they like already know what a quadratic equation like it looks like parabola. I'm just wondering, did anyone kind of try to approach this problem from kind of cubic might look like this, and then look at the numbers from the graph.
Yes. Yeah, people are definitely doing that. And you get the kind of argument that we saw with Bolzano last week, where it's sort of algebra versus geometry, that yes, that's a nice geometrical way of seeing that a cubic has so many roots, provided they're real roots. But does that necessarily tally with this more algebraic approach that people are trying to take? So yes, but there are also people who are trying to move away from that way of thinking. Okay, so just a few more slides before we take a break. So the thing that I've emphasized a few times is this reduction of degree. So people setting out to solve a cubic equation find that with certain manipulation, you end up reducing to a quadratic, which in principle is easier to solve. And similarly, starting from a quartic, dropping down to a cubic. And in fact, if you want to look at it this way, when you solve a quadratic by completing the square, essentially you're dropping down to a linear equation when you're solving a quadratic. So this pattern holds there as well. So there is a notion that emerges here of the reduced equation of a polynomial. It's called the resolvent equation in some cases. And so for a cubic, the resolvent equation has degree 2. For a quartic, the reduced equation has degree 3. For a quintic, what is the degree of a reduced equation? So we know what we would like it to be, certainly. And this is the direction that Euler goes in. So he hypothesizes that the degree, for an equation of degree n, the degree of the reduced equation will be n minus 1, just as a hypothesis. Etienne Bezout comes along a little bit later, and he revises this just based on investigating properties of polynomials, and he says, well, okay, first of all, the degree of the reduced equation for a polynomial of degree n will in general be n factorial. However, he notes that you will often be able to reduce this in some way. So he thinks, well, you usually be able to bring this down to n minus 1 factorial. And he's thinking of tricks like the thing that we saw before with Descartes' equation that looked like a degree 6 equation, but it was actually a cubic. So just noticing things like that, exploiting symmetries in equations, he's hopeful that you can bring this down to a more manageable value, and in fact, hopefully even bring it further down to n minus 2 factorial. But this is all very much a hypothesis that he's proposing, and that people then start to test out. And it doesn't quite yet bring them any closer to the solution of the quintic. But at this point we get to Lagrange, who I've already mentioned a couple of times. So 1770, he produces this enormous text, this sort of 200-page text, and presents it to the Berlin Academy, in this case, Reflections on the Algebraic Solution of Equations. And what he does in this text is he looks at all the methods that people have written down before him. So he looks at Cardano, Schoenhaus, Euler, Bezout, Descartes, everybody, and sort of pools everything that they've done and examines their methods. And he's trying to find a common thread across all of these methods in the hope that you can adapt this to higher degrees. And so the reduced equation is what he picks out as being this common thread. So just to round off this first lecture, I'm going to go back to Novi. I'm going to say I hope I've said enough to convince you that there's more to the story than this. There's a lot to say about the algebra that's going on in these 2 centuries, even if people are not coming up with new solutions. And in this connection, I have some recommended reading. So this book by Jackie Stead, also, From Cardano's Great Art to Lagrange's Reflections. So filling that gap in the history of algebra, which has this nice comment or nice description of itself in the preface: the hitherto untold story of the slow and halting journey from Cardano's solution recipes to Lagrange's sophisticated considerations of permutations and the functions of roots of equations, which is what we look at in the second half. But there's also a really nice commentary elsewhere in the preface So this kind of comment from Novi is, as she says, betrays a fundamental shortcoming of many earlier accounts of this area, and also adaptable to other areas of the history of mathematics, that we would only ever be looking for great and significant works and substantial changes. Of course, we're interested in the more incremental changes as well. As she says, fortunately, the truth is more subtle and far more interesting. Mathematics is a cumulative endeavour, which is the thing that was emphasised again and again in our classes the other week on the history of the calculus. Many people have contributed through half-formed thoughts, tentative proposals, partially worked solutions, and even outright failure. So mathematical creativity can be slow, sometimes messy, and often frustrating. But as I've highlighted above, that I think is why it's interesting to look at all this. And this is very much the sort of ethos that I'm trying to adopt in this course. Hopefully I'm managing to convey it. And when it comes to the sort of the tentative things in the middle here, I've got quite a nice example in the second half of that kind of some mathematical ideas that don't really go anywhere as such. Okay, so I'll stop there for the first half.